Welcome back to the CMCC Mechanochemistry discussions. This seminar is hosted by the NSF Center for the Mechanical Control of Chemistry, or the CMCC. The goal of this seminar series is to bring the mechanochemistry community together. The seminars are streamed live on the third Thursday of every month at 10 a.m. Central on YouTube. They're also recorded and made available on our CMCC Mechanochemistry discussions channel to be watched at any time later. We've had an outstanding set of speakers for 2020, the latest of which is today's speaker, Dr. James Mack. We're also currently lining up a great set of speakers for 2021, so stay tuned. Quick note on Q&A, this webinar is being recorded. If you have any questions during the presentations, please email them to cmccdiscussions@gmail.com, and we will migrate those to the speaker to be answered at the end of the presentation. If you have a YouTube account, you may also post your questions directly in the comments section. However, note that we do reserve the right to remove comments that do not adhere to CMCC's values of inclusion and respect. A quick but very big thanks to Dr. James Batiste, the CMCC Director, Noah Sheehan, who's helping implement this seminar series, and Jennifer Belsick, the Administrative Coordinator of the CMCC. Thank you very much for joining us. Please subscribe and follow us on YouTube at CMCC Mechanochemistry Discussions, and also follow us on Twitter for the latest updates. So now, for today's speaker, we are very fortunate to have Dr. James Mack of the University of Cincinnati. Dr. Mack earned his BA at Middlebury College and his PhD at the University of New Hampshire under the direction of Glenn P. Miller. After earning his doctoral degree, he was a postdoctoral fellow at Boston College with Lawrence T. Scott. He joined the faculty as an assistant professor at the University of Cincinnati in 2003, was promoted to the rank of associate professor with tenure in 2009, and full professor in 2016. His research has been featured in the New York Times, Chemical and Engineering News, Chemistry and Industry, as well as National Public Radio. In addition to his research accomplishments, Dr. Mack has received recognition for his mentorship and service by both graduate and undergraduate students. Today, we're very fortunate to have Dr. Mack speaking to us about developing selective reactions under mechanochemical conditions. Thank you again, Dr. Mack. We're pleased to have you speaking for us here today.
Thank you so much for the wonderful introduction and the opportunity to talk to you today about some of the work that we are doing in mechanochemistry. About some of the work we're doing on selective reactions in mechanochemistry, some of the things that we've kind of learned throughout the years as we're going in this field. Traditionally, we do our reactions in organic type reactions, and so that's what I'll focus in on for the most part. Before I do to the chemistry, I think it's important to tell you where the work is actually done. We're in Cincinnati, which is in the state of Ohio in the United States. It's right next to Indiana and Kentucky. It's roughly about 2.1 million residents in the greater Cincinnati metropolitan area. It's uniquely situated in the United States where you can kind of get to about 60% of the population in a day's drive. You can hit Chicago, Atlanta, Detroit, Indianapolis, and it's home to six Fortune 500 companies. We do the work at the University of Cincinnati, which is a public research university in the city of Cincinnati. This is a picture of a campus-wide photo. A lot of the work that we do pretty much happens in this building over here in Rivershow Hall. And just like a lot of public universities in the United States, we have a lot of area for our athletic programs. So this is our American football stadium, which is right on campus. And this year, our school is ranked in the top 10. Doing pretty well, and unfortunately due to COVID we can't cheer them on, but they're doing quite well. So that's where the research is done. And if I had to give a takeaway of what I'm going to talk about today, if there's one thing I can drill it down, is the idea that Although mechanochemical reactions seem very, very different than our traditional solution-based reaction, at least from an organic chemist perspective, it's very similar, but there are some nuances and there are some things that you must pay attention to, especially if you're going to try to do some selective reactions. Those factors are you've got to pay attention to the temperature and frequency, and I'll talk a little bit about that. There might be some mechanistic differences. Sometimes there are and sometimes there are not. So we have to investigate that. I'll walk you through an example where things are different. And the type of milling material that is being used. And I'll give you an example, and I'll go through some catalysis work that we've done to demonstrate that. So many of you are familiar with mechanochemistry, but there's a fair number that might not be familiar with mechanochemistry, where this might be the first time you're listening to a mechanochemistry presentation. And so if I wanted to kind of show the similarities between a traditional solution reaction and mechanochemical reactions to show what happens. Traditionally, we would take reagents, we put them into a round bottom flask, you'd add solvent, and the solvent would be there to break up the crystalline lattice and cause the mixing between materials. Then you would stir it around or heat it if necessary. That would cause a chemical reaction to occur, and then you'd have to remove the solvent, and then you would get the product out, and that's what you would traditionally see. In our system, what we do instead is we take the same reagents, we put them in a milling vial, add a ball bearing, add it to a milling apparatus. The ball bearing inside the milling apparatus will cause collisions between the ball and the materials. That will cause a chemical reaction, and then you get a product out. Because we're not using bulk solution, and bulk solution is traditionally representative of the large amount of chemical waste that's in many organic reactions or reactions in general, many mechanochemical reactions are inherently greener than what we would see in solution. And so a lot of what we do is also from a green perspective, in addition to understanding some of the nuances to this type of chemistry. It's always important when doing a mechanochemical seminar or writing an article, talking about the equipment that you use. So there's various types of different mills, planetary mills or shaker mills, and there's different companies of those types, and the energetics are all different. And so for us, we use a specs mixer mill, with that's depicted here. We use a combination of our homemade reaction vials and vials from Formtech. We put them inside of our mixer mill, and then we set the timer and let the reaction occur. We use different types of mills, milling vials made of different materials. The vast majority of what you'll see today is done using stainless steel, but we also do chemistry using nickel and copper as well. I'm not going to be able to have the time to talk to you about some of the nickel and copper reactions that we do, but I will talk to you about some of the silver reactions that we've worked on in the past. So if I could show a picture of what's happening inside of the mill. So in our mixer mill, this is pretty much what it looks like if it's operating at full speed. So it's going very, very quickly, and the ball bearing is bouncing around in there. If we were to slow that picture down and get a different view, so this is slowed down 20 times, and you can sort of see the motion of it. So it's not a true back and forth motion. It's more like an infinity symbol or a figure 8 turned at 90 degrees. And so in this way, we like this kind of mill because we think there's more randomization in the ball and allows for a more efficient mixing, which is going to be really, really important. So for today, I'm going to focus on 3 different areas. I'm going to talk a little bit about energetics of the system, which is really, really important when we talk about selectivity and reactions. Reaction mechanism, I'll show you an example of a traditional organic reaction that under traditional solution-based reactions goes through one pathway, but under mechanochemical conditions go through another pathway. It provides an opportunity. And then the last thing, talk about catalysis and surface catalysis using either the vial material as the catalyst or the ball as the catalyst. So if I focus on energetics, reactions typically, you need to focus on kinetics and thermodynamics. And especially if you're looking at organic reactions, we need to understand activation barriers and the difference between reactants and products. And if we focus on kinetics, we're mostly looking at the Arrhenius equation. And thermodynamics, we're mostly looking at Gibbs free energy equation. I don't have time to talk to you about some of the work we're doing on the thermodynamics aspect, but I will tell you a little bit about what we've learned on the kinetic side and how we can look at the Arrhenius equation and apply it to a mechanochemical reaction. So when we wanted to look at this, we were really interested in what the energetics of a mechanochemical reaction would look like. Where is the energy coming from for the most part, and how can we utilize that energy to do some selectivity? There were a lot of things that we were able to do, but one of the aspects we thought we needed to look at was what is actually happening on the surface while the ball is impacting the molecules on the wall. In order to do that, we thought we needed a reaction to serve as an energy probe, and the reaction we chose was the Diels-Alder reaction. And that's a cycloaddition that happens between a diene and a dienophile, and we chose that reaction because there was no reagent besides heat for the most part, meaning that if you have enough energy in the system, the reaction will occur. It's easily tunable, so you can change the activation barrier, which I'll show on an adjacent slide. We can reliably model it computationally, so we can get some good understanding of transition state barriers of these reactions. And it was cost effective, and it was pretty safe. So the molecules we used didn't pose any significant hazards. So these were the different types of Diels-Alder reactions that we looked at, and these were the calculated activation barriers that we achieved for these different types of processes. And all of these were within a kilocalorie or so between experimental results. And so we're really confident with these numbers. And our idea was we mill the reaction for 3 hours and really just see if the reaction occurred or not, with the understanding that if the reaction was successful, that would suggest that we had enough energy in the system to overcome the activation barrier. And if the reaction was not successful or did not produce product, then we did not have enough energy in the system. And we would basically just keep going through every reaction higher and higher and higher until we got to our limitation, wherever that limitation might be. So we started with this set of 6 to see where we would start. We began with this reaction because that was pretty much in the middle. That allowed us to go up or down in terms of percent yield. So that's where we started. And we basically looked at all these different types of reactions under a lot of different conditions. And so what you'll see here is each point, and if you see everything is collapsed on that point, that suggests that under all of these different conditions, it provided quantitative yield, or it gave the same result. So in this case, we looked at different vial frequencies. So we looked at frequencies from 15 hertz, 18 hertz, and 21 hertz. And we looked at different vial materials, Teflon, steel, and then we hardened the steel to see what the differences were there. And so there were 9 different unique conditions that we ran, and then we looked at what the yields were. So the reaction that was 8.9 kilocalories per mole went quantitative yield for all conditions that we looked at. And the same thing was true for the one that was 11.9 kilocalories per mole. When we got to the reaction that was at 12.8 kilocalories per mole, that's when we started to see some differences in terms of conditions, where if we use 15 hertz in Teflon, the reaction did not happen in 3 hours. Then we got 0% yield, or no noticeable yield. But if the reaction was done at a speed of 21 hertz with hardened steel, then we were able to get complete conversion. And we saw every point in between those two as well. And so that allowed you that there were some differences in milling speed and vial material. as you keep going to 14.6 kilocalories per mole, you start to see the yield go down. Then you get to 14.9 and over 17 kilocalories per mole, no matter what we did in terms of how fast we would move the vial or how hard the vial material was, we were never able to get an appreciable amount of yield. And so what we learned from this is that as we expected, the yield approached zero as a activation barrier increased. Teflon did not produce high yields compared to steel or hardened steel. And we assumed that based on some of the results we had previously. And so we started looking at this in a certain way where we thought maybe there's three separate regions we broke this graph into. There's a point in the graph where you had enough energy, enough thermal energy at least, to do the reaction under any conditions possible. And the reason that we looked at the thermal energy aspect of it is none of these reactions were done at absolute zero. So we started thinking about there's a combination of things that are going on where there's a thermal component and then maybe there's a frequency component to the energetics of a ball mill system. Then we looked at the another aspect of it, and that was if we parse out the Arrhenius equation and look at its components, if we assume that the activation barriers for this Diels-Alder reaction are the same, then we can almost break this Arrhenius equation into two different aspects. We look at this thermal component, which you have in solution, and then this frequency factor, how often do materials meet and how well do they mix together? And that is the term, and that is the area that we thought we would have in this collisionally enabled region, where that we are affecting the frequency by which they're meeting, which has an effect on the rate of the reaction. Typically in solution, what you look at is how concentrated the solution is will dictate how often molecules interact. But in here, we have complete control over that by how fast we mill the materials. We also noticed that there was a certain point that no matter how fast we moved the materials or how hard the vial was, there was an energetic barrier we couldn't overcome with these two reactions. And so there were some limitations on what we were able to do. So we thought if this was true, then it should map onto a Boltzmann distribution in some way. And so we did a calculation of the Boltzmann distribution, and we thought it should map on a Teflon. You wouldn't have that enhancement of stainless steel at all. And that, if you look at it, it sort of does that in a way. And so we thought, well, maybe if we increase the Boltzmann distribution through a change of temperature, we could get some of these other reactions that did not occur previously to occur. So that's what we did next. And so we started changing the temperature to see what happens. And lo and behold, you start seeing these other reactions occur. The temperature that was required for our highest energy to occur, typically in a 3 hour, you require 144 degrees in xylenes. We were able to do the same process at 100 degrees with frequency added on. And so what we learned from this is that our frequency is more of like a fine adjustment to some of the energetics where our temperature acts as a force adjustment. And so that allows us to fine tune some things that you can't do in a traditional solution reaction. And so we looked at this a little bit further and said, how could we apply this and what could we apply to? And so we looked at a very simple reaction, the reduction of T-butyl cyclohexanone. And so we looked at it in methanol, which is typically done, and a lot of students do this at an undergraduate level in an undergraduate laboratory when they're looking at diastereomeric differences between products. And so we looked at it in methanol and compared it to mechanochemical reaction at different temperatures. You start to see as you lower the temperature, we saw a more enhanced effect on the mechanochemical conditions. But more importantly, what we saw is the same type of trend that we saw previously. So when we ran the reaction at 40 degrees, no matter what speed we ran the reaction, we didn't see an enhancement of the diastereomeric selectivity because the temperature was too high that the little changes that we might make didn't have a global change in what we saw. However, as we start to lower the temperature and go down a bit, then you can start seeing these enhancements. And that suggested again that at every different temperature you had another adjustment, another dial you can dial up to make some other fine-tune adjustments to the energetics of the system to get where you want it to go. And so that allowed us an opportunity that we thought in solution, typically if you lower the temperature, that is how you would enhance a lot of these different reactions. But now we had an added component that you typically don't have in solution. The other thing that we learned is that since the mixing and how fast molecules meet was dependent upon the frequency, we can use frequency independent of temperature in this case, such that typically in solution, the lower temperature you go, the slower the reaction is, but we can speed up the reaction simply by increasing the temperature in that case. We also found that was a bit more complicated. So we looked at a reaction done by Sue and coworkers, and this A3 reaction, and we saw what they reported was as they increased frequency and the enantiomeric axis went down, but then they got to 25 hertz and then it went up again. And so we thought it was a good test case. They use a planetary mill, and so the frequency that they use as they increase frequency, temperature increased as well. And so we thought it's a good model system that we can use to see what adjustments we would make in our system. And so what we saw was not the same thing we saw in the Diels-Alder reaction. When we had looked at yield, when we increased the temperature, yield increased. However, when we enantiomeric access decreased. However, when we looked at the frequency component and we just looked at frequency and what the frequency adjustment would be, then that frequency that we saw didn't have a great effect on this reaction as it had in the previous reaction. And so we were looking at that and said there must be more to it. Now, this reaction used silica gel, and we have some other data that I'm not showing here that suggests, and other people have seen this as well, the rheology of materials, how well materials mix together has a real big impact on the rate of a lot of these different reactions. And so it's an added component you have to think about. So traditionally as an organic chemist, you look at classes of reactions. You say this class of reaction operates one way. And so we can look at classes of reaction. In a mechanochemical sense, the class of the reaction matters, but also the specific reagents that you're using in the reaction matters as well. And so we're trying to deconvolute a lot of these different things and try to get a better understanding of how these are all related to each other. So that's on the energetic side. I'm going to shift gears a little bit and then talk about reaction mechanism from a mechanochemical standpoint. And what I have up is just a traditional generic reaction mechanism that organic chemists use all the time. In this case, is nucleophilic reactions, whether it's nucleophilic substitution reactions or 1,2 addition or 1,4 addition. Typically, this is the types of things that we would write. A nucleophile adds into a carbon, let's say, and displaces out a leaving group. And there's a lot of generic things that we talk about. And in this case, X is representative of a halogen, and it really doesn't matter the halogen. As long as it's a good leaving group, it'll leave. And this is typically something that I would teach in organic chemistry. And you always get a really good student that will raise their hand and says, well, Professor Mack, your equation isn't balanced. And, you know, how are you doing this? And so on and so forth. And typically we don't balance the equations. And if you look at textbooks, and this comes from the textbook that we use, basically these counter ions are just there to balance the charge. So don't really have to worry about them. And since the identity of the counter ion is inconsequential, we don't pretty much put them in the chemical equation. They typically solvated out of the way, and it pretty much doesn't matter. And that's typically the attitude that solution chemists, especially organic chemists, would have. And that's something that we teach all the time. When you look at a mechanochemical reaction, you might look at things differently. When we look at bases, we do the same types of things where everything is a free ion. And so the pKa, if you will, in water is related to just this free ion going around, and there's no other things that you would have to worry about. And so many organic chemists, especially in traditional training, need to memorize these numbers and the solvent systems they were in and so on and so forth to know what base you would use under certain conditions. Well, in solid state reactions, there's a lot of interactions between different halogens and alkali metals, and the enthalpies of formation and the lattice energies are all different. And so is it a fair assessment to ignore these types of things for an organic reaction when you're doing it? And so that's one of the things that we wanted to investigate to see what the effect was. We didn't want to do a quantitative look because we didn't know if the quantitative values really that are looked at, let's say in gas phase or in a crystal structure would be similar to a mechanochemical condition or not. So then we would more look at a qualitative viewpoint of it using hard soft acid base theory or the Jones-Doyle beta coefficient, and then basically looks at if it's hard or the numbers are very similar, then they would be a good match. And if it's soft or again, the numbers are pretty similar, then those also would be a good match. And what interactions would those have from a chemical reaction standpoint? So we started looking at this chemical reaction. We used phenol really as a nucleophilic substitution type process with a base. And we made different adjustments, and we had what that X group was. Did that X group actually matter? And did that M group matter? In this case, M is going to stand for an alkali metal. And so as you see on the chart, the M does matter as well as the X. And so if you use lithium, it does not act as a really good either base or nucleophile. And our belief is that since lithium and oxygen are both hard, then there's no benefit to acting as a base in that case because it's pretty much stable where it is. Same thing with sodium. But as you go to a mismatch pair, let's say, where you use cesium, where the overlap is not as good and cesium and oxygen is not making a good ion pair in that case, then you would have a more aggressive base, and then you would and a more aggressive nucleophile, and then you would see the reactions happen. And then the pair that it would match up where cesium would match up with iodine would be the best, followed by bromine, followed by chlorine, and that's what you see in this case as well. And so we use these carbonate bases in this way, and that was something that you could use in solution. So then we looked at as well, can we up the ante a bit and use a carbonate for something that typically you wouldn't use a carbonate for in solution? And so in this case, if you look at the various different alkali metals and you use cesium, you could see cesium works really, really well as a base. And if you use two equivalents, it just happens faster to do the reaction. What we learned from this standpoint is you can use some safer bases to do some chemistry that typically would use harsher bases in solution. And so that would be a safer alternative if you can do this. But basically what we learned is you can destabilize the base, and you can destabilize certain things to cause our chemical reaction to occur in a safer way than you can do in solution. We can transition this to hydroxide ions. And so if you use hydroxide, you see the same types of thing where even here lithium hydroxide starts to work a lot better than the carbonate does. And that's the same trend you would see in solution. So just like we saw where you had a temperature aspect, and then for every temperature, you can have an added bonus there. We see the same thing here. So the way we're looking at this is for every pKa, if you will, changing the alkali metal on that gives you an added bonus before you get to the next base in the system. And so now that provides you more opportunities to do things that you couldn't do previously. So how can you use this type of process in, let's say, mechanistic type of standpoint? So if you go to a traditional Wittig reaction, and there's been a lot of work that we've done on this, and I'm not going to go through it all, I just don't have the time. Typically, you take triphenylphosphine in this case, or phosphine and alkali halide, and make this phosphonium salt. You add a base. In this case, we'll add benzaldehyde in a base. That'll deprotonate the phosphonium salt to provide a nucleophile, which will add into the benzaldehyde to generate this betaine intermediate. This betaine intermediate goes to an oxyphosphate intermediate, and that causes the two phenyl rings to occupy the same side of the oxyphosphate. Then you have an elimination occur, and that will give you this cis stilbene as the product and triphenylphosphine oxide. And so this is an old traditional reaction people use all the time. And then there's modifications to try to get to the trans version and so on and so forth. Well, if you look at this intermediate, again, you have these free ions, and that's typically what you would see in solution. When you're undergoing mechanochemical conditions, you do not have a solvent available to you. Here you have these ions going through the same type of process. You're going to have a base, and here we're not going to use a hydroxide. We're going to use a carbonate, which is going to be a little safer. Since we don't have solvation, now our potassium and our oxygen are not solvated out of the way. So they must participate in the mechanism such that this interaction, this alkali metal halogen interaction, has to be important in the mechanism. And now, since it's a 6-membered ring mechanism, these two groups don't wind up on the same side. They wind up equatorial to each other on that 6-membered ring, which will wind up on opposite sides. And so that should give you a trans stilbene and deoxyphosphane. And then you're going to have this alkali metal halogen pair in the process. And so if you look at what we find, it's exactly what you expect. The lithium bromide does not have a really good interaction, so we get no product there. Same thing with the sodium and bromide. Very similar to what we saw on the previous slide, but now we're moving this towards a reaction that needs these two to interact in order to be successful. And then when you look at potassium and cesium with the bromide, you can see the stilbene does occur, and you see it mostly with trans stereoselectivity. If you change it to chlorine, then you look at the chlorine and you start to see the sodium chloride interact, and you see a diminishing yield on the cesium and chlorine because that interaction does not happen as successfully. And so one of the things that we wanted to look at is can we switch the stereoselectivity between it simply by adding a little bit of ethanol in the system or not doing liquid assistant grinding. And so if you do add a little bit of ethanol in the system, you get to mostly Z stereoselectivity with pretty good conversions. But we saw when we didn't have any ethanol at all, we got the trans stereoselectivity, our conversion wasn't as high. And so we wanted to try to change that. And what we are able to do is find out if you add ethanol in the first step of the reaction, you could get a high amount of the phosphonium salt. And then if you let the ethanol evaporate and do dry mechanical conditions in the second step, that will get you the high conversion with a high trans stereoselectivity. And so we were able to basically take this Wittig reaction and simply by doing liquid assistant grinding conditions or not, switch the stereoselectivity to mostly a Z stereoselectivity or cis stereoselectivity to a mostly trans stereoselectivity with pretty high yields and conversions. So the last thing in a few minutes that I have left is to talk to you about some metal catalyzed reactions that we have been uncovering. And so here what we used is we use these diazoacetates in the presence of styrene to do cyclopropionation reactions. And these reactions are pretty important for making these strain ring systems, and people use them all the time. We were looking at a bunch of different types of metals to do these reactions, and we settled in on silver because that gave us the highest yield and it gave us very good stereoselectivity. So pretty much mostly the trans stilbene is what we saw in this process and gave us pretty high yields. The good thing about this is that we recycle the metal. So typically when you do catalysis in this way, the metal is a casualty and the reaction is not recovered. And so a lot of times, especially with homogeneous catalysis, the goal is to get high turnover numbers and use as little catalyst as possible. Well, in these systems, that's not our goal because we are not going to lose our metal in the system. And so we can use it over and over and over again. And this is just an example of using it 5 times where we can get pretty high yields in this process. And we don't have a loss, a significant loss in mass of the silver foil. Although this says 5 times, we've used this hundreds of times by now. This is some older data. And we still have the same piece of silver foil that we've been using constantly over and over and over again for all of these different types of reactions. The other thing is that silver is relatively cheap compared to the catalyst because there's not a whole lot of effort into making the catalyst itself. So it's just really just silver foil that you're using. And so here's just an example of different substrates that we can use on the diazoacetate side to make different types of cyclopropanes in this system. And then we moved on to looking at if we can make cyclopropenes in our system, and we can. So this is traditionally the types of catalysts that would be used and how much these catalysts cost per gram. And this is what we've been able to deduce. So what we found is if you use a copper catalyst and using copper foil, they are very selective for terminal alkynes. And if you use a silver foil, they're selective for internal alkynes with pretty high yields. And we can recycle these multiple times in our system. So here's an example of using silver in an internal fashion. I'm not going to go through all of these different substrates, but for the most part, it's pretty reasonable. You get high yields and high selectivities with silver. If you use copper for terminal alkynes, you see about the same thing. So it's very you can get a diverse set of molecules this way. So then we wanted to look at selectivity again. So we had these enines. We looked at these enines and we looked at it and said, well, can we selectively make a cyclopropane in the presence of an alkyne? And can we selectively make a cyclopropene in the presence of an alkene? And so we were able to do that. If you use silver, it'll have selection to make the cyclopropene. And if you use copper, it has selection to do the cyclopropane. So again, we're looking at selectivity that we're in the same molecule. You can utilize different metals to selectively go after different materials. One other thing about this that's important to note in this project, if you take diazoacetates that are highly reactive, like this unstabilized diazoacetate, if you're using DCM, which Davies did, then this is the product you get. So basically you get insertion into the methylene chloride as the major product. It's just simply too reactive. When we don't have the methylene chloride, we just have a substrate that's not an option. And so now you get to this product that you can't get to in solution. Same thing happens when you have a very stabilized diazoacetate. You make the carbenoid and then that undergoes dimerization, where we avoid dimerization because we have a lot of really good mixing, and so we can get it to add to our substrate instead. So that provides some context in terms of some of the things for these types of reactions, the difference between some things that we identify in solution and some things we identify in our milling system. We moved along and thought, well, maybe we can look at this process and then do a one-step, one-pot Shonagashira reaction, where if we take a terminal alkyne, if we can do Shonagashira reaction in silver, that'll make an internal alkyne, then that same silver can then make the cyclopropene. So then the first thing we did was look at, can we do Shonagashira reaction silver mediated, and we were able to do that. And so then the next thing we wanted to look at, can we add everything into the system and get out this cyclopropenated substrate, and we were able to do that. Well, the first step of the reaction is the Shonagashira reaction, and that goes from the terminal alkyne to the internal alkyne, and then we have our substrate readily available to decompose down to the carbenoid, and that will give us the cyclopropene. So we were able to make a library of molecules in this way, which was really neat process, and allows the ability to make a diverse set of molecules in a pretty simple way. It's important to note that all of the reactions that were done, all of them were done at ambient temperature and ambient atmosphere. So there were no nitrogen based reactions or dry, quote unquote, dry conditions needed, where typically if you do this in solution, you would have to undergo inert atmospheric conditions to do this chemistry. The last thing I'm going to do is a really quick plug. So we've learned a lot of different chemistry and a lot of different things about selectivity. And so I had a student who graduated that Joel Anderson, who did a lot of the kinetics work, that started a startup company looking at a lot of different reactions and trying to increase the speeds of reactions under mechanochemical conditions for the pharmaceutical industry and any other industry that needs to do that. This is the website if anyone's interested or have needs based on that. But you can see on the graph, we can definitely increase a lot of certain types of reactions in mechanochemical conditions as compared to solution. So that's all I have time to talk to you today about. So hopefully I was able to convince you that strategic use of frequency and temperature can lead to a much better control of reactions and form the solution. The use of ion pairs, something that organic chemists typically don't think about, can be a great ally in the development of reactions that are more selective than we see in solution, or you can change the selectivity of certain reactions by either adding solution in a liquid system grinding mode or removing it. Metal catalysts, in addition to frequency and temperature, can be used for these reactions. And our whole goal all along in terms of philosophy of our group is if we can understand the rules that govern some of these reactions, we'll be able to do some things and predict our reactions and try to get to a different place than we know about currently. So with that, I will conclude and thank all of the people that actually did the work. I had a great class of students over the years that have done this, and some wonderful collaborators that have worked with me on these projects. And thank you so much for the invitation and your attention, and be happy to answer any questions.
All right. Thank you very much, Dr. Mack. We have just a few questions for you. First, regarding the vial surface characteristics, do you expect properties like surface roughness to affect reaction rate?
I do. That's one thing that we haven't looked at as much as I'd like to, but I think the roughness of the surface is going to be important. When you look at heterogeneous catalysis, these imperfections on sites is one of the things that people have noticed is where the activity actually happens. And we've seen some things in the past that have suggested that. One of the cool things about ball mill reactions is by definition, you create a lot of these rough surfaces. And so we take that to our advantage, but definitely we think that's a part of the secret sauce to what we've seen.
Great, thank you. The next question is, for Diels-Alder reactions at different frequencies, is there a way to relate frequency or milling speed to activation energy so that in the future we can use frequency to determine activation barriers of reactions? Does your, this is multi-part, so let me just quickly finish. Does your Diels-Alder work provide a calibration curve for exactly this? In other words, does frequency of milling only affect the pre-activation factor, or does it also provide energy?
That is a question that we're still trying to determine. And I believe the answer to the question is yes. However, I'll put a caveat out there. And that was one of the goals that we want to do. And there's some data I haven't shown because that's exactly what we wanted to do. So if you look at that equation, we do think there's an energetic component to the frequency. We think it's a small energetic component as it relates to the temperature. We think that, like I said, it's a fine-tune adjustment. However, it's hard to decouple that from the mixability. So when you look at the frequency factor, there's a lot of things that we're learning that's involved in that. Frequency is one of them, so how fast they're able to meet. But the crystalline lattice is another one. And so you have to break down the crystalline lattice. So you might be going faster, but there might be certain reagents that have a stronger crystalline lattice than other reagents. And so then the ability to break down that crystalline lattice is not an apples to apples comparison, more of an apples to oranges comparison. In addition to that, since there are two components, there are sometimes components that we know if we mix them together automatically goes to a melting depression or eutectic mixture without any mixing at all. It just magically happens in that way. And there's other components that doesn't happen. So we're trying to deconvolute all of these different factors to get to something like that, but it's really challenging to deconvolute all of it. And so what we're trying to look at instead is how can we say what factor of frequency would have in a certain reaction versus a true correlation in that way. But that was our goal, but unfortunately, it's a little bit more complicated than that.
All right, thank you. We have just one more here, or we have just time for one more, I'll say. For the diastereoselective reaction on T-butyl cyclohexane, mechanochemistry affects the product distribution. This suggests that force favors one transition state over another. Why do the addition of force and increased frequency affect one transition state over another?
So that is where I think the energetics of the mill come into play. So if you look at any of these selective reactions, at the transition state is where that difference is. And so typically when you try to do it thermally, you're trying to find that sweet spot of where the difference in the transition state energy matches that thermal energy. And that's typically what you're trying to do. Here, we're trying to do the same thing. And I think the energy component, the amount of energy that's transferred to the transferred to the molecules, provides that small difference of energy that is going to go to do these reactions, and that's going to overcome one activation barrier, then another activation barrier because of that difference. Along those lines, though, is that particular reaction is slightly exothermic. And so one of the things that we have to consider is, although we believe that the ball in frequency is providing its own energy, there might be some energy that's being transitioned from molecule to molecule that, as we control the rate of the reaction, limits how much energy is transitioned that's released from one molecule to maybe another molecule. And so those two things we're trying to deconvolute as well. But I agree that the frequency provides some small amount of energy, and our goal is to use that small amount of energy on other systems to provide more selective enantioselective and diastereoselective reactions than you can get in solution with temperature alone.
All right, excellent. Thank you again for being part of the CMCC Mechanochemistry discussions, Dr. Mack. We really appreciate your contribution. I would like to thank you both on behalf of about 80 people attending live, as well as all those who will watch you in the future as we post this on YouTube. So thank you again, Dr. Mack.
Thank you so much for the invitation, and look forward to hopefully interacting with everybody out there on a lot of different things in the future. And mechanochemistry is a burgeoning field that has a lot of unlocked potential, and I think a lot of people are truly realizing the potential it has. And I can't wait to see what happens moving forward.
Great.
Thank you.
Thanks again.